For the longest time, mining asteroids was just pure science fiction, right? Something out of a movie. Well, that is changing, and it's changing fast. What was once just a dream is now becoming a serious engineering and economic reality. We're on the cusp of a huge shift in how we see our solar system, not as this vast, empty void, but as a brand new frontier for industry, for enterprise, and for absolutely incredible wealth.
And that number you see, that's not some fantasy figure pulled from thin air. That's the estimated value of the precious metals in just the asteroids that are orbiting relatively close to our planet. Getting our hands on even a tiny fraction of that could fundamentally reshape our entire global economy.
So, what's the big deal? Well, it all comes down to concentration. See, here on Earth, we have to sift through tons and tons of rock to get a tiny amount of precious metal. But these asteroids, they're different. They're basically the leftover building blocks of the solar system, meaning all those precious metals can be found right there on the surface, just waiting to be picked up. Okay, so you're probably wondering, why now? What makes this a serious conversation all of a sudden? The whole economic case really rests on two incredibly powerful drivers. One serves our needs right here on Earth, and the other is all about building our future out there in space. Let's dive in. What's really fascinating is that there are two totally different prizes we're chasing out there. On one hand, you've got these platinum group metals from what we call M-type asteroids. They're absolutely critical for our electronics and for the green energy transition, but they're incredibly rare here on Earth. And then, on the other hand, you have water from C-type asteroids. And in space, water isn't just for drinking. Oh no, it is the absolute currency of exploration. It's liquid gold. And this is where the economics get just mind-blowing. Here on Earth, water is basically free. But getting that same water into orbit, every single kilogram costs a fortune to launch against Earth's gravity. So if you can harvest water that's already in space, you completely eliminate that massive cost. And here's the kicker. You split that water into hydrogen and oxygen, and boom, you have the most powerful rocket fuel we know of. You've just built an interplanetary gas station. All right, so the why is pretty clear, right? The potential is massive. But what about the how? I mean, how do you actually do this? We're not talking about sending up astronauts with picks and shovels. This is going to require highly autonomous robotic missions designed specifically for the weird challenges of microgravity. Let's take a look at the playbook. First things first, you've got to know what you're hunting for. C-types, the carbonaceous ones, there are cosmic gas stations absolutely loaded with the water ice we need to fuel an in-space economy. Then you have the M-types, the metallic ones. These are the flying treasure troves, the literal remnants of ancient planetary cores, packed with valuable metals. And S-types are more of a rocky mix. Picking the right target is the absolute critical first step. Now, no matter which type of asteroid you're going after, the mission plan basically boils down to these three simple steps. First, you prospect. You find and analyze your target. And missions like NASA's OSIRIS-REx have already proven we can totally do this. Then you extract, using some of the really cool techniques we're about to look at. And finally, you utilize that material, either right there in space or eventually back here on Earth. Okay, let's get into the nitty-gritty. Method number one. This is how we go after those flying treasure troves we talked about, the metal-rich M-types. This whole process is just so clever because it uses the space environment to its advantage. A small robotic refinery lands, and it uses mirrors to focus sunlight into this super intense beam, melting a patch of the surface. Then, in microgravity, the molten metal droplets can be just plucked out with magnets, separating them from the rock. This isn't science fiction. This is a technique that companies like Asteroid are building and testing right now. Okay, that's how you get the metal. But what about the water? The real currency of space. Well, for that, you need a totally different approach. And honestly, it's surprisingly elegant. I love this method because its genius is in its simplicity. It's not about brute force, it's all about finesse. You basically wrap part of the asteroid in a big bag. Then you gently heat the surface with sunlight. The water bakes out as vapor, and that vapor naturally floats over and freezes onto these cold panels ready for collection. It's a technique called optical mining, and it's being pioneered by TransAstra. So the first two methods are all about bringing the factory to the asteroid. But what if you could flip that script? What if you could bring the entire asteroid to the factory? Yeah, that's the third plan, and it's by far the most audacious one. The idea here is to target smaller asteroids. We're talking 10 to 100 meters across, and just capture the whole thing. Using these super-efficient ion engines, a spacecraft would slowly, gently nudge it into a stable orbit near the Earth or the Moon. And once you have it parked nearby, you can bring in the really heavy-duty processing equipment that you only have to launch once. You're turning a distant object into a local, easily accessible resource. Okay, I get it. At this point, you might be thinking, this all sounds great, but it's pure sci-fi, right? Decades away. Well, here's the thing. The foundational tech isn't just on a drawing board somewhere. A lot of it has already flown. This is happening now. Just look at how this has unfolded. It's a story of accelerating progress. We went from international treaties that set the basic rules to crucial national laws. That 2015 U.S. Space Act was a complete game changer because it gave companies the legal right to actually own what they mine. That's the incentive you need for billions in investment. And now, with missions like OSIRIS-REx, we have the scientific proof of concept. The very next step is commercial demonstration, and that's just a few years out. The momentum is undeniable.
And that's the key takeaway here. We are not waiting on some magical new breakthrough in physics. All the critical puzzle pieces are already on the board, and they're flight-proven. We have the super-efficient ion engines we need. We've mastered autonomous navigation to rendezvous with an asteroid millions of miles away. We even have the legal frameworks in place. The challenge isn't about invention anymore. It's about engineering, integration, and finance.
So, let's zoom out. What does all of this really mean? What's the ultimate payoff? Because it's not just about bringing a few tons of platinum back to Earth. It's about something way, way bigger. It's about fundamentally changing our relationship with space itself. This is what it's all building towards, a true in-space economy. And that creates this incredible, self-sustaining loop. Asteroid water creates cheap rocket fuel, which makes more ambitious missions cheaper, which allows for even more mining. This is how we break our total dependence on Earth, and it's how we finally start building big things in space for space.
And think about what that enables. The downstream effects are massive. With resources already in orbit, refueling a satellite could suddenly cost 90% less. Building a permanent base on the Moon or launching a real mission to Mars becomes dramatically cheaper and more sustainable because the fuel, the water, and the building materials are already waiting for you right where you need them.
And that brings us to this final thought, which I think just perfectly captures the real goal here. The true value, the first real trillion-dollar prize, isn't going to come from what we bring back. It's going to come from what those resources allow us to build out there. The first trillion will be made by creating the infrastructure, the gas stations, the factories, the raw material depots, that finally makes humanity a true multiplanetary species. So, that's where we are. We're standing on the edge of this new frontier. This isn't a dream for the 22nd century. The technology is proven, the resources are just waiting. The first commercial missions are literally being planned for the next few years. So the only real question left is, how quickly and how boldly are we willing to seize this opportunity?